try it out today. All right, so the first thing I want to talk about today is something I hope that you sort of know, but people forget these words, is you have to know the different classifications of real numbers. So natural numbers, whole numbers, and integers, you might think those aren't important vocabulary words, but they are, because if you see a problem that it requires only integer answers or only whole numbers, you have to know the difference between there. So does anybody know the difference between whole numbers and integers? I bet whole number you can tell me. What's a whole number? Counting numbers, yes. So like what to start with? That's the difference between natural and whole numbers. Natural numbers start with 1, ... Like remember when you probably don't remember, but when you were in the preschool, probably you didn't learn to start counting with 0 because you didn't talk about 0 for a long time. My son used to have this play mat that had all the letters and then numbers 0 to 9. And the picture said you could put 1 through 9 and 0 to 8, but I could have really actually 0 to 9. And then whole numbers are the counting numbers starting with 0. No negatives, no fractions, no decimals. The whole numbers. Yeah, you could just type it in. Especially if you know what stylus too, right? Yeah. But there.
Yeah, so I'm trying to write whole.
All right. And then people always get confused with integers because in elementary school you skip over integers and you start talking about rational numbers. You talk about fractions way before you talk about negatives. But integers are just all the negative whole numbers and the positive whole numbers. So integers still don't have fractions and still don't have negatives, but they include, I just said that. They still don't have fractions or decimals, but they do include negatives. So I like to write it as like ... -3, -2, -1, 0, 1, 2. So one of the big things between Algebra 2 and Precalculus is I really try to give you some of the math notation. If you're going to go into a math or science field, I think that you should get used to seeing some of the math notation. So up until Precalculus, probably rational numbers are just defined as any number that can be written as a ratio or a fraction. Right, that's kind of the key word, is a ratio. I wrote down here terminating or repeating decimals. If it stops or it repeats itself, it can be written as a fraction. But a nice math definition of a rational number, and I kind of wrote all this for you, but this is set builder notation. It's any number in the form a over b such that a and b are integers. So any integer over another integer is a rational number. So most numbers you can think of probably are going to be rational numbers. Like 7 is a rational number because you could write that as 7 over 1. 2/3 is a rational number, right? Any fraction you can think of, any decimal that stops or repeats itself. And then we have that other category of numbers, irrational, which basically just means not rational. And so pi is our favorite irrational number. Hopefully last year you learned about the number e when you talked about logarithms. That's a less known irrational number. But also any square root or any radical, I guess, that's not a perfect root. So like the square root of 5, the cube root of 7, right? Anything that doesn't work out to be a nice integer answer is actually a number that is irrational and it's just going on in a class. And so on the next slide, I think I stole this from the Algebra 2 book. It has that lovely like diagram to show that these are kind of subsets of each other, right? And I don't really need to write all this out. Write anything on this slide. But the natural numbers are kind of like the smallest set of numbers because it just starts with 1 and goes on forever. Like it still goes on to infinity. But do you agree that the rational numbers, which Q is the letter, I always forget what letters are used for this. The rational numbers include all the integers, all the whole numbers, all the natural numbers, plus all those fractions that don't fit in those. So in a class I took once with a bunch of nerdy people, we talked about like that different things, like there's bigger infinities, right? Like you think infinity is like as big as it gets, but like all of these go on forever. There's infinitely many, but the set of rationals is a bigger set of infinitely many than the set of natural numbers. Do you agree with that statement? Ever thought of like levels of infinity before? Yeah, and it's true. Some infinities are bigger than others. And it's true, definitely in math. But I like this chart, and I think it's helpful. I'm not going to give you, in Algebra 2, I give it on my first test, I make them classify numbers. I'm not giving you that, but this is vocabulary that will be used a lot, and I just want you to make sure that you, if the directions say give only integer answers, it's expected that you know what integers mean. Alright, so I think it's worthwhile. Here's what your homework is basically over today besides exponents. And I never know how much the Algebra 2 teacher enforces the infinity brackets parentheses stuff when you're talking about domain and range. But in this class, that's how we write domain and range pretty much always, is using interval notation. And most college classes that I've seen expect you to know interval notation. And so I kind of wrote all the options here. And hopefully after we do one, you're going to be like, oh yeah, I remember that. So every inequality can be written as an interval. Every domain and range can be written as an interval. We talk a lot about domain and range in this class. So if I said every number between A and B, including A and B, that would be the same as saying bracket A to B. Have you seen stuff like that? So like if I said 3 to 7 bracket, that means every number between 3 and 7, including 3 and 7. So it's just kind of a shorter way than writing it in. And so these are all bounded. And maybe you can see the difference between bounded and unbounded. Is bounded has an endpoint at both sides of it, right? But the difference is whether or not it's included or not included. So an open interval is everything between A and B, but not including A and B. So the way we show that is with parentheses A to B. It's not a coordinate. An ordered pair, that's saying like the domain, we could say everything between 3 and 7, but not including 3 and 7. And then it always makes me laugh that your book calls these half open, because I feel like your book's trying to be very positive, because I could call them half closed just as well, right? It just means one side has a parenthesis, one side has a bracket, and you just need to make sure you know that if it is included, it has a bracket. If it's not included, it has a parenthesis. So kind of space in it. So this one would be what? Bracket A. Well, how are you going to write an infinity sign? You're not going to be able to type that smart. You're going to have to use your stylus and make it. And this one would be just the other way, parenthesis A. And tomorrow, not tomorrow, Thursday, I'm going to give you some problems and kind of talk about different rules a little bit more. Lots of times with domains and ranges, we have infinity in there where it goes on forever in one or both directions. And so we call those unbounded because they go on in one direction or the other. Being on the computer, we kind of don't get our practice with infinity signs, but hopefully you feel pretty good. Mr. McClure, who used to be here, taught kids to make infinities by just putting two circles next to each other, and I went and yelled at him because I did not approve of that method of teaching you to make infinity signs. That you can make it infinity, but you can't. You can practice with your stylus, I guess. Make infinity signs. Or some people make an 8, like they turn their paper sideways and make an 8 and then turn their paper back again. That seems like a lot better to me. Alright, the greater than, people usually do better with those. If I start at some number and I'm going on forever, then the left side is always your lower number. So this would be from A, including A, but going on forever. So from A to infinity. And I put a parenthesis next to infinity because infinity can't have a bracket next to it because it goes on forever, right? A bracket means it includes that number. Infinity is not a number, it's more like a concept. When my son was about 5, he asked me what the largest number of infinity was. And my husband gave her this look like, no, there you go. But I was like, well, there is no largest number because infinity is not forever. And one day he's like, Mom, I know the smallest number is 0. And my husband gave her the look. So I was like, well, actually, there's negative. I just couldn't lie to him and say, like, remember in elementary school when you're like, 2 minus 3, and your teacher's like, no, you can't do that. I was alive, like, he just lied to you. Or in Algebra 1, when his vice said, you can't take the square root of -4, and then last year, you learned it was live, like, you could, it's imaginary numbers. Like, I just can't lie to my kid about numbers. I lied to him about Santa Claus, but not about numbers. Alright. Alright, so x is greater than a. What am I going to write for that? Your letters up there, right? A is the number. X is greater than a number. Alright, when it's less than, that's the ones that people mix up because they want to say like b to negative infinity. But when you have an interval here, it has to be the smallest number first and the biggest number second. So if you're going to negative infinity, you have to start with negative infinity, right? Like it's not correct to say b to negative infinity. That doesn't make sense because you can't end at the smallest possible thing. So for this one, I'm going to say I'm ending with b, right? B is as big as it gets, and everything less than that, it's negative infinity to b. So just remember that negative infinity is always the left side. Oh, look, I did that wrong, right? What's wrong? Oh, no, I did it right. I was thinking I needed a bracket there, but I have the bracket, right? B's with the bracket. That's not, I was about to put a bracket on my infinity, but that's wrong. So this one would just be not included. So that would be negative infinity, that's as small as it gets, up to B bracket. So that's saying from B, everything less than that. And hopefully what you saw last year with most equations, most functions, the domain of most of the things we deal with is all real numbers. And so you can write it into that notation and you can use that little fancy R, but to me all real numbers is the easiest one to write in interval notation because it's just negative infinity to infinity. So that means every real number is infinity. If you look in the back of your book to solutions to problems, anytime they involve inequality or domain and range, they always do interval notation. And so definitely on your first test, I'm going to require that you do interval notation. And then after that, we can talk about if you want to write set notation, you can. Sometimes interval notation is a lot. But especially in this first test, I want to make sure that you know how to do that. And so that's what I have with your homework today. And I just have a couple quick examples to just make sure that we know how to do this. And so it says describe and graph the interval. Describe doesn't mean you have to say everything less than or equal to 2. They're wanting you to use those words like bounded, unbounded, open, or closed, which may be some new vocabulary that you haven't used before. So since this just is everything less than or equal to 2, is that bounded or unbounded? Unbounded, because it's not two numbers. And since it includes 2, is that open or closed? Yeah, so even though it's only one side, we still say that it's closed because the one endpoint that's included is unbounded and closed. And then if you look at the homework, or if you've already looked at the homework, you're going to see that when you graph these, they're a little bit different in the way you graph up until this point. Up until this point, you've always used an open circle or a closed circle to show whether the 2 is included or not included. But now it's even easier, I think, because you're going to use a bracket or parenthesis depending on whether it's included or not included. What's great about the homework online is they're pre-made graphs. You don't have to make them. When I make my graphs by hand, I usually, at most, put 2 numbers. I put 0 and I put the other number. Or sometimes I'm really lazy and I just put a 2 in the middle of the graph and I don't put anything. But sometimes I go like this, 0, and then I put a 2. And if it's everything less than or equal to 2, right, then I know it's going to be like shaded this way. The new part for you is it's included, so don't make a closed circle there. You're actually just going to make a bracket to show that the 2 is included. Kind of how you would write that interval notation, you would end with the bracket there. So I think if you know interval notation, it makes the graphing really easy. So on this one, I'm just going to make from -3 to 3. And again, if it's in interval notation, I think that it's super easy because you just take the intervals and you just put them on your graph. So -3 to 3 means I'm going to put a bracket on each one of those, and it's everything in between -3 and 3. Questions on that graphing part? Is this bounded or unbounded? Bounded, and is it open or closed? Or half, I guess. Are the endpoints included or not included? Included means closed. Open means it's not included. Alright, I don't know how much you remember your exponent rules, but I have people in calculus that forget their exponent rules, and so I just put these on here. They are in your book, page 8, in the first section there. But I just wanted to go through these, and it's always much easier if they're not letters, but this is the formula-wise. So I'm just going to write these real quick, and it's up to you if you want to write them out or not. But when you multiply with exponents, remember you add those exponents into the same base. So kind of like a little rap. U to the m times u to the n is u to the n plus n. Are those not on your screen? I deleted it. Not this? This slide. Okay. And when you subtract the same base and they have exponents, I gave an answer. When you divide, you subtract. So same base, so u to the m divided by u to the n is just u to the n minus n. Anything to the 0 power, lots of people think it's 0, but remember it's really 1. Maybe the most confusing math rule of all. And remember that negative exponents, mathematically correct stuff, we don't usually leave our answers with a negative exponent. What does a negative exponent mean that you need to do? Yes, you're saying it. Yeah, like it means it goes to the denominator, right? So when I was student teaching in Algebra 1 and I taught this, the teacher there, she was really nerdy too. And she said the negative sign is your ticket to cross the fraction bar. Right? So she was like, if you have the negative exponent, it's your ticket to move down, and then you turn your ticket in. So no, it's not really. A negative exponent really just means like the reciprocal, so that's why it goes on the bottom. If you have a negative in the bottom of your fraction, you go to the top because it means so you and then over here, I feel like this one should be next. But when you multiply an exponent to an exponent, you actually multiply those. So u to the n is really u to the n times n. So over here you add, but right here, an exponent next to an exponent, you multiply. And then the other two, they're kind of like the distributive property, but it's really not the distributive property. But if you have a product or a quotient with an exponent, you have to give that exponent to everything. So the product here, you have to give u to the m and v to the n. And the same thing with the quotient, u to the n divided by v to the n. And I just gave you a couple examples of those to practice, and I want to actually give you some time to work on this. So I'm going to just skip my last examples here because I want you to just be able to practice these. And on the homework page that we were at yesterday, which I think is wrong on your notes here, and I already stated as PDF, I didn't change it again. It's mathxlforschool.com. And if you haven't bookmarked it already, I think you should. You're going to go there a lot. And I want you to try to complete that homework. And if you haven't completed orientation, you can do that. You want me to help you? Just like I think I was trying yesterday, I think this is this class, some of my other classes, and some of the graphing on the orientation homework, I can help you. But this homework, I think there's like 8-ish questions, 10 questions, that I want you to complete. And the great thing about this homework is you'll know the letter help you get through these input problems, so you miss it. You have too much interest to do it. But it's just reviewing this implementation stuff. And again, if you're a senior, you'll have time to do some stuff tomorrow. I don't know how long the meetings will last, so if junior meeting is over early, then you guys